Hey guys, it's Peyton. Let's look at the connection between quadratic functions and square root functions. We're going to see how to get from a quadratic function to a square root function and vice versa. We're going to use the methods to find the inverse of a function extensively, and we're also going to look at the special properties of inverses. Let's do a quick review of how to find the inverse and the properties of an inverse with respect to the original function. Here are the steps to find the inverse of a function. Step 1. Switch the variables. Replace y with x and x with y. Solve for y, and then use the vertical line test to determine if the equation is actually a function. These steps are pretty easy. The algebra can get hairy and messy, but that's okay. We can overcome it. Now let's look at some of the special properties of functions and their inverses, particularly the relationship between the domain and range. Here's the main thing. The domain and range for the functions flip for the inverse function. What was the domain for the original function becomes the range for the inverse function, and what was the range for the original function becomes the domain for the inverse function. Pretty neat, huh? Okay, let's work through some examples and we'll see these properties. Here's our first one. Find the inverse of the function y is equal to the square root of the quantity x minus 4 plus 2. First step, we want to flip the variables. Where we have x, we want to put y, and where we have y, we want to put x. So our equation now becomes x is equal to the square root of the quantity y minus 4 plus 2. And now we solve for y. First thing I'm going to do is subtract 2 from both sides, so I will have x minus 2 is equal to the square root of y minus 4. And then I'm going to get rid of that radical by squaring both sides. So I will have x minus 2 squared is equal to y minus 4. Let's FOIL the square on the left-hand side of the equation. And that will FOIL to x squared minus 4x plus 4, and that is still equal to y minus 4. Now we add 4 to both sides to isolate y, and our equation now becomes y is equal to x squared minus 4x plus 8. And we're done. Let's look at some graphs in order to determine the domain and ranges. In this graph, the red function is the original function, and the green is a possible inverse graph. Okay, let's look at first the domain of the red function. I claim the domain is x such that x is greater than or equal to 4, and the range is y such that y is greater than or equal to 2. Okay, let's look at the domain and range now for the inverse function. I say the domain is all real values, and the range is y such that y is greater than or equal to 4. Alright, we got a problem. The range for the original function is not the same as the domain for the inverse. But that's just a minute mistake, because the range and the domain should flip. So maybe our graph is wrong. Let's flip the domain and range like we should, and then graph the inverse function. Here's a reminder of the information. The original function is y is equal to the square root of the quantity x minus 4 plus 2, and the inverse function that we have found is y is equal to x squared minus 4x plus 8. The domain for the inverse function is x such that x is greater than or equal to 2, and the range for the inverse function is y such that y is greater than or equal to 4. And here's the graph of the correct inverse function along with the original function. Great! This follows the domain and range properties that we determined earlier. We're done. Now, there's another way to determine if the graph we have is in fact the inverse. Remember how when we find inverses we reflect the graph across the line y equals x? Let's take a look at that using our previous example. This is the graph of the original function in red, the incorrect inverse function in green, and the line y equals x in brown. Now, if we reflect the red graph across the brown line, we don't get the entire green graph. But if we look at this graph, we can see if we reflect the red graph across the brown line, we receive the correct green graph. This is a good way to check and see if we have graphed the inverse function correctly. Now let's look at a special property of the x and y values flipping. First, let's look at a table of values for f of x, our original function. I have x here from 4 to 12, and then I have the corresponding correct f of x values, or the y values. Okay, if the special inverse property is correct, the x and y values should reverse. Let's look at a table of values for the inverse of f of x. Here, x and f inverse x are plotted in the table. And the x and y values reverse like we said they would. That's great! Now, what was the coordinate point 4, 2 for the original function is now the coordinate point 2, 4 for the inverse function. Looking at the graph, we can see the reversing of coordinate points because of the reflection across the line y equals x. Okay, let's work another example now. Find the inverse of this function and graph it. Y is equal to x squared plus 6x plus 13. Where the domain and range are given as x such that x is less than or equal to negative 3, and y such that y is greater than or equal to 4. Now we need to solve this equation for its inverse. First, we'll interchange the variables. Where x was, we'll put y, and where y was, we'll put x. So our equation becomes x is equal to y squared plus 6y plus 13. Now the question, how do we solve for y here? We could try a straightforward grunt and grind attempt, but trust me, it's not worth it and it's not going to work. However, there is a trick up our sleeves we can use, the vertex form of a quadratic equation. Remember the vertex form of a quadratic equation has just one variable each? This is our ticket in. We will use the completing the square method. Let me show you. We have x is equal to y squared plus 6y plus 13. First, we will isolate the ay squared plus by, then complete the square. I will do so by subtracting 13 from each side, and I will have x minus 13 is equal to y squared plus 6y. Now we take half the value of b, square it, and add it to both sides of our equation. Half of b here is 3, and 3 squared is 9. So the equation becomes x minus 13 plus 9 is equal to y squared plus 6y plus 9. Now we simplify a bit and complete the square, and by doing so we'll have the equation x minus 4 is equal to the quantity y plus 3 squared. Now we solve for y. Let's take the square root of both sides of the equation, and the square root is plus or minus the square root of x minus 4 is equal to y plus 3. We want to isolate y now, so it becomes y is equal to plus or minus the square root x minus 4, and we have a minus 3. Okay, we're nearly done, but now we need to determine which sign sits in front of our square root function. Let's take a look at the domain and range of our original function and use those to determine the correct sign. The domain and range for the original function is x such that x is less than or equal to negative 3 and y is greater than or equal to 4. For the inverse function, we flip these. The domain becomes x such that x is greater than or equal to 4, and the range becomes y such that y is less than or equal to negative 3. Looking at the range for the inverse function, we notice that it is always negative and always less than negative 3. Now take a look at the inverse equation. Y is equal to plus or minus the square root of the quantity x minus 4 minus 3. Okay, we want y to always be less than negative 3. So I claim there should be a negative sign in front of the square root. So it will be y equals negative 1 times the square root of the quantity x minus 4 minus 3. And we're done. But we can check ourselves some more by looking at the graphs. Here's a graph of the original function. Now, here's a graph of the original function, a graph of the inverse, and a graph of the line y equals x. Notice the red graph is the original function, and the green line is the inverse of the function. Also, if we reflect either across the line y equals x, we'll receive the other graph. We're done. Now let's take a look at a table. Here's f of x. I have x from negative 3 to negative 11 and the corresponding f of x values. Now according to the inverse trick, the x and y values should reverse. Let's look at a table of values for the inverse function. Hey, the values are flipped like we thought they should be. Looking at the graph, we can see this reversal. Let's work one more example. Y is equal to x squared minus 9. The domain is all real values, and the range is y is greater than or equal to negative 9. First step, let's reverse the variables. So the equation now becomes x is equal to y squared minus 9. Now we solve for y. First we add 9 to both sides, so it becomes x plus 9 is equal to y squared, and then we take the square root. So it becomes plus or minus the square root of the quantity x plus 9 is equal to y. Let's take a look at the graph of the original function. Also, let's take a look at the table of values for this function. We'll notice that there are no restrictions on the original function. Now we need to determine, for the inverse, if we need both the plus or minus sign or just one of them. I say we need both, and here's the graph. Okay, the green graph is the original function, and the red graph is the inverse graph, but it's not the inverse function because it fails the vertical line test. Also, to see if it fails the vertical line test, we can look at a table of values for the inverse graph. Looking at the table, the x values don't map to a single y value. They map to two different y values. This is because of the plus or minus sign in front of the inverse equation. So the inverse we have is not an inverse function, but it can be the inverse graph. So a little bit of pickiness, but this is important. And that's the end of this lesson. Remember, when solving for the inverse, to interchange the variables and solve for y. Also keep the domain and ranges in mind at all times. If you want to, look at a table of values and reverse the x and y values. And last but not least, you can always reflect the graph across the line y equals x. That's all you'll need, guys. I'll catch y'all next time.